students. Okay, what we're going to do now is actually apply the stuff we've been doing in the last few videos to real-life problems called optimization problems. So what we're trying to do is take a real-world situation, and we're basically trying to either find the largest possible solution or the smallest possible solution. So again, if you're looking at trying to maximize profit, you got a formula for that. You can use optimization to figure out, for example, what price you should put onto a product to maximize your total income. So here's the process for doing so. If it's a question involving, for example, area or volume, the first thing you might want to do is draw a diagram. Sometimes you can't draw a diagram, but if you can, highly recommended that you do. And make sure in the diagram you actually put in all the information you know and the things that you don't know. Once you got the diagram drawn, what you have to do is go from a problem written to you in English, you got to turn it into an algebraic equation, and then if the equation that you have has more than one variable in it, you then have to do some algebra to actually rewrite the equation so it only has a single variable. And sometimes this can be the trickiest step in the whole process. So you might have, for example, the area of a rectangle that you're trying to maximize, but area is half base times height. So you can't find the derivative of that function until you either rewrite it so you only have a b for base in the equation, or an h for height. And the question will give you enough information to allow you to do that, but sometimes this can be the trickiest step, is getting an equation with just a single variable. Okay, once you've got that done, find the derivative of the function. Hopefully that's going to be relatively straightforward. Set it equal to 0 and solve the equation. And now you know that you have found the local maximum or local minimum or a point of horizontal reflection. So the next thing you have to do is find out whether it is a max or a min or a point of horizontal inflection. So determine the nature using either the first derivative test or the second derivative test. And then finally, the last thing you have to also do is say, well, I found the value of a local max, for example, but I better also find out the values at the endpoints, because it might just be that the values at the endpoints of the domain actually are larger than the one that I just found. So you also have to determine the global maximum or global minimums by going to the endpoints and then just comparing those to the local max or local min. So let's go ahead and do this. Okay, so here's our question. What is the smallest possible value of a positive number plus its reciprocal? So there's no diagram to draw for this one. Okay, I can't figure out how to draw a diagram for that. So in this case, we can skip step 1. Okay, let's write the function. It's given in words. So this, again, can sometimes be a bit of a tricky step. How do you get from the words to the equation? So in this case, not too hard. A positive number, I'll call it x, plus its reciprocal, so plus 1 on x. So that's step 2 started or done. There's the function written, the question written as an algebraic function with just one variable. Now what I have to do next is find the derivative. So I'm going to rewrite 1 on x as x raised to the negative 1 power. The derivative of that, derivative of x is equal to 1. Derivative of x to the negative 1 is negative 1x to the negative 2. And rewrite that. So we have the negative sign, negative 1 becomes minus, x to the negative 2 becomes 1 over x squared. So that's step number 3. Step number 4, set that equal to 0 and solve for x. So in this case, I'm going to bring the term 1 take x squared to the other side to make it positive. I'm now going to multiply both sides by x squared to get rid of the fraction. And what number squared gives us 1? Well, keep in mind this has to only be a positive number. So the only solution to that is x equals 1. So that value of x is either going to give us the local maximum, the local minimum, or a point of horizontal inflection. So our next step is to figure out which one of those it actually is. So there's my derivative function. I just rewrote it a bit more neatly. So that's the derivative of the original function. I've got to find the second derivative because I'm going to use the second derivative test. So the second derivative, derivative of 1 is just 0. Derivative of x take 2 is negative 2x to the negative 3. So that should be x to the negative 2. Derivative of that is negative 2x to the negative 3. But because I've already got a subtract there, that becomes plus. So I've got positive x to the negative 3. And therefore I can rewrite that as 2 over x cubed. Okay, let's plug in our value of x from step number 4. And that just gives us, that's a pretty ugly looking 2. I'm going to make that look a bit more neat. Ooh, I don't want red though, I want blue. That's a bit better, not much. Okay, so that's 2 over 1 cubed. So the second derivative is positive 2. I don't think that actually helped very much anyhow. And therefore, that actually is the minimum value, which is what we were hoping to find. Okay, finally, and this is a little bit tricky for this one, we've got to then look at the values at the endpoints of the domain. Okay, but the domain goes all the way from 0 out to positive infinity. So in other words, it doesn't have any endpoints. Well, I suppose 0 is an endpoint, but no, it doesn't have any endpoints because x cannot equal 0. X has to be a positive number, and there is no number that is just bigger than 0. So there is no endpoint on the left, there is no endpoint on the right, and therefore we don't have to check for endpoints for this particular equation, and therefore x equals 1 is the smallest possible value. Okay, I'm going to stop the video here, and then we're going to do another one that involves a volume.